All the graphs we've seen so far have always had one variable neatly solved for in terms of the other variable. But what if getting one variable by itself is difficult, or even impossible? Can we still find the slope at any point of the curve? Of course we can. And partial derivatives hold the key. "2008 was an interesting year, to say the least, when it came to finance and economics. That's when the financial crisis that had been brewing for some time finally came to a head. But while many institutions were dealing with the Great Recession, something new was born in the shadows. On October 31st, Satoshi Nakamoto released a paper online that explained how to implement a decentralized form of currency, not linked to any bank, using open source software to secure and verify its transactions. This new currency was called Bitcoin, and ever since then, it and other so-called cryptocurrencies have taken the financial world by storm. The crypto in cryptocurrency stands for cryptography, which is the study and practice of encoding and decoding information to keep it safe from nosy third parties. The particular kind of cryptography that Bitcoin uses is actually based on a peculiar class of graphs called elliptic curves. Elliptic curves are described by the equation y squared equals x cubed plus ax plus b, for some numbers a and b subject to a particular condition. They come in many different shapes and sizes, but here's what a typical one might look like. This one is y squared equals x cubed minus 4x plus 1. Now, believe it or not, the study of equations like this one can be traced all the way back to the ancient Greek mathematician Diophantus of Alexandria. But it wasn't until 1985 that they were first starting to get used for cryptography. The way people use elliptic curves for cryptography involves a very strange kind of addition, where we take 2 points on the curve, draw the secant line between them, find the third point where that line hits our curve, and then flip that point upside down to get our sum. Now, if that seems a little weird, don't sweat it too much. Just take my word for it that this can be called addition. But if we want to add a point to itself, instead of finding the secant line between 2 points, we need the tangent line at 1 point. Yep, we need calculus. But how do we do that with a curve like this? I mean, y is definitely not a function of x. The curve doesn't pass the vertical line test. Even if we do try to find an explicit formula for y, we get an ugly plus or minus square root, which makes computation and derivatives much more difficult. And that's kind of disappointing, since when you look at it, the equation of elliptic curve is pretty simple. It's just a polynomial. Polynomials are nice, and they're supposed to have nice derivatives. We like the power rule. So, what can we do? Well, luckily for us, there is a way to find the derivative without having to solve for one variable first. Instead, we can leave it as what's called an implicit equation, which means that x and y can be anywhere in the equation we want. Think like how the equation of the unit circle is x squared plus y squared equals 1. That's an implicit equation, because we don't have either x or y isolated on one side in terms of the other variable. We'll look at what happens with the unit circle first, and then see how what we find applies to the elliptic curve. Okay, first of all, just to see what we're up against, let's see what happens if we do try to get y by itself first. If we subtract x squared from both sides, and then take a square root, this is what we'd get. Y equals plus or minus the square root of the quantity 1 minus x squared. Then, to take the derivative, we'd need to rewrite that square root as a 1/2 power, and then apply the power rule while also remembering to use the chain rule. Yikes, that's way too much work. So, let's see if we can find a better way to do it. let's think of the left side of our equation, x squared plus y squared, as a function of two variables, x and y. If those variables change by a small amount, then how does our function change? That's the total differential we talked about in the last lesson. So let's find that. If we let x change and y stay the same, then the derivative of x squared is 2x, and the derivative of y squared is 0, since y is a constant. So the first term is 2x times the differential dx. Then, if we let y change and x stay the same, then the derivative of x squared is 0, since now x is a constant, and the derivative of y squared is 2y. So the second term is 2y times the differential dy. So our total differential is just the sum of those two, 2x times dx plus 2y times dy. Now there's one issue. If x and y can both change by any amount, then there's no guarantee that we'd stay on our circle. To make sure that happens, we need to preserve the relationship between our variables. X squared plus y squared has to always be equal to 1. So that means that if the left side changes, the right side has to change along with it. So the differential of the right side has to match the differential of the left side. Well, since 1 is a constant, the differential of the right side is just 0. So if x and y change by a little bit while staying on the curve, we have 2x dx plus 2y dy equals 0. And that fits our intuition, by the way. If x squared plus y squared is always equal to a constant 1, then that sum should never change, even if the point we're looking at does. Now, let's use a little algebra to rearrange this equation and figure out the slope dy over dx. Start off by dividing both sides by dx. Dx over dx is just 1. So now we have 2x plus 2y times dy over dx equals 0. If we subtract both sides by 2x, divide both sides by 2y, and simplify the fraction that we get, we end up with dy over dx equals negative x over y. That's a formula for the slope at any point of our circle, or more specifically, the slope of the tangent line at that point. No pesky square roots or plus or minus signs needed. The technique we just used is called implicit differentiation, since it lets us find the derivative when our equation is an implicit equation, where you don't have to have one variable isolated in terms of the other one. But as with many things in math, there's a trade-off. Here, the catch is that since y may not be a function of x, you actually need to know both the x and the y coordinate to find the slope. So for example, since the point 3/5, 4/5 lies on our circle, our derivative formula tells us that the slope of the tangent line at that point is negative 3/5 over 4/5, which simplifies to negative 3/4. By the way, you might remember from high school geometry that the tangent line to a circle is always perpendicular to the radius. And that's also the case here, since that's the negative reciprocal of the slope of the radius. It all checks out. Okay, now that we have an idea of how implicit differentiation works, let's try it out on our elliptic curve from earlier. You might want to pause the video here and try to work this out yourself before you move on. All right, ready? Here we go. First, let's take the total differential of the left side. If we let x be our variable and y be constant, then the partial derivative of y squared is 0, so we won't have a dx term. But if we let y be our variable, then the partial derivative of y squared is 2y. So all we have on the left side is 2y times dy. Okay, now let's try the right side. If x is our variable, then the partial derivative is 3x squared minus 4. So all that gets multiplied by dx. And if y is our variable, then all of those terms are constant. So that partial derivative is 0. We don't get a dy term here. So the right side is just 3x squared minus 4 all times dx. And in order to make sure we stay on the elliptic curve as x and y change together, those two sides of the equation still have to be equal. Alright, now we just do some algebra. Divide both sides by dx, and then get rid of the 2y by dividing that out, and boom, the derivative, the slope of the tangent line at any point of our curve, is 3x squared minus 4 all over 2y. So, for example, the point -1, 2 lies on this elliptic curve, so if we plug that in, we find that the tangent line at -1, 2 has a slope of -1/4. So that's how implicit differentiation works. First, take the total differential of both sides, differentials times partial derivatives all added together. Then, use algebra to solve for dy over dx. That usually involves dividing both sides by dx and then shuffling some terms around. Now, one last side note about elliptic curves in cryptography. You might have guessed that the elliptic curve we studied here isn't actually the one that Bitcoin uses. And you're right. The one Bitcoin uses is actually this: y squared equals x cubed plus 7. Yes, seriously, that's it. The entire security of Bitcoin rests on this simple little polynomial. The catch, though, is that all of the calculations are actually done using something called modular arithmetic, which means that you wrap back around after you get to a particular number. You actually use modular arithmetic every day when you tell time. If it's 9 o'clock, then 4 hours later it'll be 1 o'clock. So 9 plus 4 is 1, mod 12. But Bitcoin doesn't do mod 12. It uses a much larger mod, which it turns out is actually a prime number. Yes, that really long number is in fact prime. Large prime numbers have been essential to cryptography for a while now. They let us do calculations that are very hard to undo, even by computers, which is what makes their codes easy to use, but hard to crack. And using a prime number actually means that all the calculus stuff we've been talking about still works, including implicit differentiation. There's a lot more to elliptic curves in cryptography than what we've talked about here. We've only barely scratched the surface. But it shows how even abstract mathematical curves and equations can find a use in the real world, and a pretty high-profile use at that. So I guess the takeaway here is don't discount some piece of math just because it's abstract. The application just might not have been invented yet.